Hello and welcome. We are live at the Pluralsight Author Summit at Pluralsight headquarters in Utah. I'm Matthias Anderson, one of the developer advocates at Pluralsight, and I have with me here Michael Perry. And we're going to talk today about some CRDTs, which we'll explain in just a minute. But first, let's start with just getting to know you a little bit, if you don't mind, Michael.
Yeah.
Do you want to tell us a little about yourself?
Yeah, thanks, Matthias. I consider myself a software mathematician. What I love to do is to apply the rigor of mathematics to creating correct software. My first course in the Pluralsight catalog was provable programming, which we did 10 years ago. And it was just really all about how you could know that the software you're writing is correct by using some mathematical ideas that have been published for quite some time. Just bring them to bear on the topic.
Yeah, I mean, that's really valuable stuff. Obviously, mathematics is foundational to computing, both in terms of the computer's functioning, but then also in terms of computing science is based on the things that we can learn from mathematics and so many different things in computing science, the data structures like we're going to talk about today, or algorithms and whatnot. We get benefits from that, encryption, security, all sorts of stuff. So I guess one of the things that I would ask you is, we were talking earlier about CRDTs. Do you want to just give a really high-level overview of what a CRDT is so that we can start there?
Yeah, absolutely. So any data type like that you would use, like a linked list, it's really just structure and operations. So these are how things are organized in memory, and then these are the operations you can perform on them. A CRDT is a little bit different in that set of operations and that structure is running on several different machines all at the same time. Now, two machines can't simultaneously know the same thing at the same time.
Right.
The only way that they can understand what's happening on another machine is by receiving some kind of a signal. And so it's not that we have taken one data structure and distributed it magically across several different machines, but instead the rules of a CRDT are such that you can have some assurance, some mathematically provable assurance that over time, after every machine has received the same amount of information, that they will reach the same conclusion. And that's a pretty powerful assertion.
It is really powerful, and so there are two sides to that. There's obviously the side which is the theoretical, the science, can we prove about it, and then there's the side of it which is now we can put it into practice and we can use it and make value from it. Do you want to give us just a little bit of a sense for then what are some of the value points of a CRDT? Like where does that come into play?
Yeah, so some CRDTs that you might be familiar with. There's one called Crdt, which is a text editing collaborative CRDT. So imagine that you and a friend are using a collaborative editing tool, and you type something in, they type something in, and after some time has passed, what you see on your screen is different from what they see on their screen. That would not be a very good experience. You want that assurance that they both converge to the same text. So that's a really good place where CRDTs show up in our daily lives, but that's not the only place. In Git, for example, that's a way that developers can communicate, can collaborate with one another, and they're doing so by just working autonomously on their own machine, and occasionally sending signals to other machines by doing a push and a pull, and yet everybody eventually agrees on the same commits being in the same branches, so they've got the same picture of the history of the source code. So really anywhere that you can use software and you can use computers collaboratively, CRDTs can really be quite beneficial.
Yeah, there definitely are a lot of very valuable applications. So I'd like to dig into that in just a minute. I just wanted to also mention that since we're live streaming here, I'm getting some of the chat comments up on my screen here. Some people from Texas and talking about the math and engaging. So I appreciate that. I wanted to let people know that if you do have some questions, we might even be able to get a chance to answer some of them while we're live. So take a look at that. But I wanted to get back to one of the things you were mentioning that, so those were two very different applications of CRDTs. One of them was a live situation where you have fairly low latency, and the other one is a very asynchronous situation. So the editing the same document, you want that to synchronize very quickly together, and I assume that there might be some differences, but maybe also some similarities. With something like Git, where you have a repository and you have multiple people working against it, I think that one of the things that comes to my mind is clock synchronization really isn't something that you can use, right? You can't rely on any sort of real-time conflict resolution. You have to really deal with it at the fundamental data level. So I know that hashes are such a critical component of how the Git repos work. Do you want to, does that spark something you want to make some comments on there?
Yeah, absolutely. The reason that hashes are so awesome is that they are based entirely on the content. There's a related topic to CRDTs called content addressed storage.
Okay.
And this is where you take, for example, you take a photograph, and you take a picture with your phone, and it gives it some weird name. But if you take a look at the name for the next photograph, it's just the next number up. So it's coming up with the name that doesn't have anything to do with the content. So that means that if you then move that to your machine, you rename it, then you pull photos off your phone again, you might get a duplicate. But if instead what the phone did was it took the actual binary of the photograph, and then computed a hash of that binary, and then used that as the name, then every time a machine came up with a name, they would come up with the exact same name. In fact, any machine in the world that came up with a name would come up with the exact same name. So it's location independent. It doesn't matter where you are, what machine you're on. You're going to have the same identity. And if you change the photo in any way, you change the scale, you do a touch-up, you just enhance the image somehow, you're going to come up with a different hash. It's going to be a different identity. So not only are hashes location independent, but they're also they support immutability. So you cannot change the thing without changing its hash and therefore its identity. And now bringing that back to CRDTs, immutability plays a really crucial role in making sure that several different machines all understand that they're talking about the same thing. So if you avoid those incrementing numbers, if you avoid things like GUIDs even, and instead go with the hashes like Git does, then you get the benefits of immutability and synchronization, not in the terms of time, but in the terms of understanding that we're talking about the same thing. And that really helps distributed systems to work.
Yeah. So your mentioning of immutability reminds me of the cache invalidation situation, and they say that there are two hard problems in computing science: naming things and cache invalidation and off-by-one errors. But the cache invalidation is really such a key thing to make sure that we are using correct information at that point in time. And if we can say that it's based on the data like you're describing, then we can be confident that the cache is correct because it is tied to the data itself and not just to some point in time.
Yeah.
So it's actually a really powerful tool that we can get a lot of benefit out of. We use it in Git for repositories, and one of the things we were talking about when we were chatting about this earlier was the conflicts that we have in Git versus the conflicts in the data type. The data type we're talking about is conflict-free, replicated data type. So do you want to talk a little bit about the conflict there as opposed to the conflict in Git?
Right, yeah. Yeah, conflicts in CRDTs take a slightly different definition. They are really bad things. You don't want to have a conflict in a distributed system because a conflict, the way that we're taking it here, means that two different nodes will come up with the same with different answers for the same question, and they will never come back into agreement.
Right.
They are always going to be in conflict. What instead we want is eventual consistency. So we want eventually for everything to come to an agreement. And so a conflict in Git is something temporary. It's, I made a change, you made a change. Okay, we just made concurrent changes, but they can't be brought back together to make a compiling piece of source code. But somebody can resolve that conflict, and then everything is good again. So that kind of conflict is actually not the kind of conflict that a CRDT avoids. In fact, Git is a CRDT. The lack of conflict is the fact that everybody's got the same branches. So this code is allowed to branch, but the merge operation in Git actually creates new information. So it takes this branch, it takes that branch, and then it tries to merge the intent of those two code changes. And sometimes it takes a human to really tell the computer what the intent was and to correct that conflict. But that's not the sort of conflict that a CRDT avoids.
Yeah, and I think one of the really interesting things there is that Git is not about tracking a single copy of your source code. Fundamentally, it's not about one tree that is your source code. It is about all of the changes that aggregate to create whatever your current head is, whatever your current branch is. And that is what you're using, but all of the history is that CRDT that actually enables a lot of the functions that we were talking about the asynchronous editing capability. And that's very, very interesting stuff. By the way, we have some people saying hello from West Africa, so hello back to you as well. And someone was also asking, are CRDTs used in very large-scale machine learning? Like, is there an application where it could come into the ML or AI sort of space, or does that sometimes get handled in a different way, do you think?
That's often handled in a different way. The difference in the problem is with large-scale machine learning, you've got basically the entire model all in one place, so that it could all be executed. And it's very tightly interconnected. So it would be very difficult to define a CRDT that represents a change to a model, and it wouldn't really be addressing the same kind of problem. Now, you might build a model out of data that you mine from a history, like for example, GitHub Copilot, based on GPT-3 was then further trained on the corpus of data that is GitHub, and that's a whole bunch of commits, a whole bunch of changes to source code. So that could be the input to a model, which can then give us some really cool insight, but you wouldn't implement the model itself with CRDTs.
Yeah, that's really interesting. Actually, the GitHub Copilot has been coming up a lot in a number of discussions, and I'm sure the rest of you out there have been having discussions about this if you've come across it as well. But I guess one of the things that that now that you mentioned that makes me think is it being trained, or was it trained on the final source code, or was it trained potentially on some of the commit history that sort of led up to that? That'd be kind of an interesting thing to me, because the data's there, and I don't know the answer to that. But
yeah, I think that it was trained on the final source code, not on the commit history. But yeah, imagine the kind of things that it could learn based on the commit history. Is that when I'm changing this part of this source code, I also tend to change that part as well. Actually, maybe Pluralsight's offering there for analyzing your commit history might be a good way to do that.
Interesting. Something to look into. Yeah. Yeah. So I don't know if people out there have any other questions, but we have maybe a couple more minutes here. But was there something else that was on your mind about the CRDTs at all to sort of because obviously you've been thinking about this a lot, right? And we were having a really great conversation, so we decided we should share it with a live stream. So I'd love to hear some more insights if you want to share.
Yeah, absolutely. In fact, I've been thinking about it for so long. I wrote a book on this topic. It's called The Art of Immutable Architecture.
Nice.
So immutablearchitecture.com. You can find information about the book. And I use CRDTs as a way to model business processes. So the way that I do that is a technique I call historical modeling. Let's take a decision that's made in a business process. So the decision to purchase a product, and then what follows that decision. Maybe the invoice for that purchase. Another one would be the shipping of that purchase. And so those are two records that then point back to the purchase itself. And that forms this graph, this directed acyclic graph, where all of the arrows, all of the predecessors are pointing back to prior decisions, things that happened in the past. And so the evolution of the graph itself is a CRDT. It is conflict-free because each time you accrue new information, you just merge it into the graph. You don't overwrite, you don't delete, you don't replace any data. All of those historical facts are immutable. And so once that fact is recorded, the fact can't be changed. But a successor might change how you interpret it. So the graph grows into the future. So in this book, I show how you can draw a historical model for a business process, turn that into a data model, turn that into messages for a message bus, turn that into an API, and show you different patterns for how you can use this modeling technique most effectively.
That sounds really cool. I don't know if there's going to be a course upcoming about that, but that sounds like an interesting possible Pluralsight course.
Yeah, I sure hope so.
But so did you say it was immutablearchitecture.com?
Yes.
Okay.
Yes,
so
correct.
we should definitely get the link in the description there as well. But awesome. That immutable architecture is such a powerful technique. I'm glad to learn about your book. I should go get it myself. So unfortunately, I can't get it right now, so you could sign it for me. But maybe we'll have to work something out later.
So I'll be back next year.
There you go. There you go. We've got a question here about the Git data type. Someone was asking, but Git doesn't signal from remote servers to subscribers that have cloned from it. It's a polling only system. Would signaling here make feature branches or Git flow work better, avoiding trunk-based development?
They might. So the strict definition of a CRDT doesn't mean that it has to be real time. So we were talking about real time collaboration. That is a real time example, but Git is not. But they're both CRDTs. What the formal definition just means that your data type has three functions. It has three operations. One is update, where you add new information to it. The other one is merge, where you take information from another CRDT and you merge it into your own. And that merge can happen in real time. It can be push or it can be pull. It still meets the definition of a CRDT. And the third one is project. And that is where you take this internal data structure, like all of these Git commits that are all pointed back to one another, and then you project that into something meaningful. Like in the case of Git, you project that into the current version of the source when you're looking at a particular branch. And so you can use these operations in a real-time push protocol. You can use them in pull. It would be kind of interesting to run that experiment with Git to see if I were to push changes in real time to your machine, would you be able to use that information while you're on a different branch to change what you're doing and collaborate better? I'd be willing to try that experiment.
That is an interesting idea, yeah. So one of the projections that you mentioned for Git is the current version of your source code, because you're wanting to get the files and compile it or do something with it. But I imagine another one of the projections is something like the Git blame or annotate, right?
Yes,
So
yeah.
what happened in that? What happened to this part of this piece of source code, looking back through the history, because then you can get that information using the commits leading up to it. So,
Yeah.
are there any other projections that that sort of come to mind that would be good examples? Or
Oh wow, yeah.
sorry to put you on the
Yeah,
spot, but yeah.
I think, the analytics that we were talking about before, like understanding who is best at a particular area of the code, or take a look at through your commit history and see which areas of the code are most frequently touched. Maybe even do some analysis comparing when somebody touches this, they also touch that. So maybe these are tightly coupled areas of the code that could use some work. So yeah, that's another form of projection that could offer some really valuable insights.
Yeah, very interesting stuff. Well, I really appreciate you taking the time to chat with us here. We've had a good conversation, and I'm sure a whole bunch of people are going to be taking a look at immutablearchitecture.com and taking a look at the stuff that you've made. Also, your courses on Pluralsight. Actually, while we're still live,
Yeah.
do you have a course that you want to mention that you've made for Pluralsight that you think people would get interesting value out of?
Yeah, I just finished up EF Core 6 Best Practices. That was a really fun one. There's not a lot of CRDT stuff going on in that one.
Fair enough.
But Distributed Systems Fundamentals. That one does have a historical modeling in there, and I talk about how you can derive messages and then use those. In that example, I use mass transit as the example message bus to build a distributed system. So that's a pretty fun course.
Awesome. Well, thank you. I'll echo what people have been saying in the chat as well. Thank you for presenting this information. Thanks for your participation in the chat. And I see one person saying they need more stickers for their laptop. So you should find us at an event, and we'll hook you up with some stickers. But thanks for joining us for this stream, and hope you join us for the next one. We're going to be having some more streams today, and you can check out some replays from yesterday. But that's pretty much what we got today. Thank you again very much, Michael. We really appreciate it.
Thanks, Matthias.
All right.